So at this point, we know a lot about the different kinds of conformations that are out there. We know how to use our Newman projections to represent them in 2 dimensions, the 2 different kinds of Newman projections, eclipsed and staggered. If you go back into your notes right now and take a look at the 6 different conformations we drew for ethane, you'll see that we have a difference between the eclipsed conformations and the staggered conformations. You should have 3 of each, alternating between eclipsed and staggered as you go through the series of 60-degree dihedral angles. We learned that when blue and red were as far apart from each other as possible, or 180-degree dihedral angle, we call that anti. And when they're right next to each other, just at the cusp of being able to engage in a lot of van der Waals strain, we call them gauche primarily. We also referred to the strain in the bond itself as it twists as Pitzer or torsional strain, and we also called the interaction of steric strain, which is almost always the term that's used instead of van der Waals strain, steric strain as the avoidance of atoms because they're all coated with electrons from each other, like repels like, of course, in this universe, opposites attract. And the reason that we're able to categorize the different energies is when something is in the staggered conformation, it's quite a bit lower in energy than eclipsed because we're avoiding these 2 kinds of strain. Again, steric or van der Waals strain as the atoms begin to overlap with each other, and Pitzer or torsional strain, which is the twisting motion in the center bond. All we have left to do to complete our tour of conformational isomers and give you a chance to do some practice problems is move on from our friend ethane, which we've been using quite a bit, to butane. And I promise you our drawings are going to be very, very similar because we are going to use an old model kit trick. Here, instead of just writing blue and red, I'm going to write methyl blue and methyl red. And that gives us the ability to change our structure from C2H6 to C4, and that would be 6 altogether, 7, 8, 9, H10. Now, this is a very important point to make because I've maybe told just an eensy-weensy bit of a half-truth to you. When we're following along with the different energies of these conformations, the truth of the matter is that hydrogen atoms are so small, and remember, these were really just colored hydrogen atoms. We weren't using any special extra functional group. H. There actually is no van der Waals strain, or if you will, let me try to use my eraser here again. That's embarrassing, more embarrassing than usual. There is really no van der Waals strain in between 2 H atoms. But if you want to get super technical, what we'll say is it's so minuscule that there is no reason why 2 H's can't be eclipsed with each other. And the bottom line on that situation is that ethane is freely rotating along its single bond between the 2 carbon atoms all the time at standard temperature and pressure. If there were some ethane in the room, which I'm guessing there is right now, it's constantly in a state of rotation and there's really nothing we can do about it. When we get to even a slightly larger functional group, in this case going from ethane to butane, I swear that's supposed to say butane, going from H to methyl makes it so that we have a completely different energy profile. And if we redo our conformational analysis from last time following methyl red and methyl blue instead of just our blue and our red H atom, again using Professor Newman's idea of the creepy eyeball and staring straight down the rotating bond, we're going to see something very, very different in this case. So even though I know it's a little bit pedantic, let's draw all 6 of those conformers just to get some more practice while we're taking our notes. And again, I'm going to ignore using all the H's. So our first conformation will look like this. In this case, we're going to call this methyl blue. And we will start, to match the drawing that I've already done, I'll get rid of that. And we will start with our staggered conformation, which has methyl red already behind methyl blue. We will rotate through 60 dihedral angle degrees, And the next conformer we draw, if we keep the front atom in the same orientation, should be staggered with methyl red right here. Another 60 degrees. Keep methyl blue in the same place. This time we're going to be back at doing a staggered conformation, or pardon me, a eclipse conformation, only methyl red is now down here on the right. Let's do another 60 degrees. 3 more to go. Keep methyl blue in the same orientation. This time we'll be drawing the anti-conformation. They're 180 dihedral angles apart. That is the methyl blue and the methyl red. If I continue to rotate, and again, keep my methyl blue in the same orientation, I'm back to having another eclipsed conformation, only this time methyl red is over here. And last but most certainly not least, I go back to another staggered conformation. Again, methyl blue still up top, and now methyl red is here. You should be able to label, using some of the terminology we talked about before, each one of these different conformations. Of course, if we complete another 60-degree turn, we end up right back where we started with. You should recognize that our friend right here is what we referred to as the anti-conformation. The methyl blue and the methyl red are exactly 180 dihedral angle degrees apart. You should also recognize that this guy and this guy are what we called gauche. This is because the two functional groups we are paying attention to are 60 dihedral angle degrees away from each other, and that's how we track all the things that we're looking at with regard to the different dihedral angles between methyl blue and methyl red. And what we are going to do is attempt to come back to this slide a couple times, and even though it sounds like it's an impossible task, it ends up being one that's almost too easy. We're going to attempt to plot, now that we have this difference in size between H's on ethane bumping up against each other and methyl groups on butane bumping up against each other, we're going to attempt to plot the total energy involved and all of the infinite number of conformations that are possible. Yeah, you heard me right. We're going to do everything we can to plot this number of conformations here in just about 5 minutes. The only way that we can actually do that is by assigning energy values to each one of the conformations that we see. So what we're going to need to do is write down a few energy values. There's really only one we've talked about so far, and we will measure these values, by the way, in the classic organic chemistry, kilocalories per mole. It's not xcals per mole. This is supposed to be a K. I will be mindful and try to get rid of it. There we go. So in kilocalories per mole, two H's being on top of each other in an eclipse conformation, we've already said it's a small number, it's a real number, but for all practical purposes, there's no van der Waals strain there. They don't care if they get too close to each other because H's are so small. When they're eclipsed, basically it costs us 0 kilocalories per mole. The same should be very obvious to you, must apply to two H's being gauche, because at this point they're 60 dihedral angles away from each other, and that's even further than when they're eclipsed, basically right on top of each other when you use your model kit. If they're gauche, they're also going to be 0 kilocalories per mole. Things start getting interesting when we start involving methyl groups, because again, an H atom on its own is just about that big in our little drawing here. That means a carbon atom is quite bigger and has 3 H's of its own when we're looking at a methyl group. When we're talking about comparing the size of an H to the size of a methyl group, they're quite a bit different. And since there's even more electrons involved, we're actually going to start seeing some problems, like when H's and methyl groups get eclipsed. That actually is quite energetically costly and comes in at about 1.92, if you want to, kilocalories per mole. Interestingly, because the methyl groups are kind of off rotating on their own, when H and methyl groups are gauche to each other, this actually is going to cost us just about, again, 0. Actually, the number is real and it's a little bit higher than that, but it's just about 0 overall. If you've been following along, with everything we've talked about in terms of conformational isomerism, then you know that I definitely should be writing one of the biggest numbers on our chart right now. When two methyl groups actually get eclipsed with each other, not just with another H, but with each other, it's going to cost us 4.5 kilocalories per mole, and that is quite an amount. In the same vein, we would not expect methyl-methyl interactions when they are gauche to actually clock in at anything other than 0, and it ends up being about 1, let's say 0.9 for all of our energy values. And why this is interesting is it gives us the ability to go back and chart energy values for each one of the conformations that we've already looked at, okay? So let's do that conformation by conformation, starting with the first one where they were both eclipsed. The they, of course, that I'm referring to, I've already drawn the wrong conformation. Pretty classy. I do appreciate with you guys putting up with me trying this method of lecture for the first time. As always, I am open to your interpretations of whether it was helpful to you or not, knowing full well that one of the acceptable answers is, that sucked, never do it again. If we put these two eclipsed to each other and we take a look at our energy values, we're actually looking very, very seriously at plotting this conformation at 4.5 kilocalories per mole. You have every right to ask me, how did you know that that was true? This interaction, according to our energy chart, is worth 4.5 kilocalories per mole. However, every HH interaction that we have is worth 0 kilocalories per mole. So if you want to, it's as if we just added 4.5 to 0 plus 0, and that pretty much covers everything that we need to talk about for this, conformation. If I move to the next conformation of butane, keeping methyl blue here and methyl red here, we end up with a few other kinds of interactions, and we want to make absolute sure we keep track of those energy values as well. We've got a number of HH gauche interactions, 2 H-methyl gauche interactions, and 1 methyl-methyl gauche interaction. So by my estimation, there are 3 completely different things going on here. We want to check our energy values. I think the first one to remember is that HH gauche is 0. H-methyl gauche is 0 as well. So really the only one we need to worry about is the methyl-methyl gauche, and the total energy value for this conformation clocks in again at 0.9 plus 1, 2, 3, 4, 5 times 0. Since 1 and 2 interactions are worth 0, and the number 3 interaction is worth 0.9. Of course, we have 2 conformations that look like this. Methyl red can also end up on the other side, and that would actually be the same energy value for this conformation as well. What other conformations are out there? What about the anti-conformation? In this conformation, we go back to our energy chart and we really don't see any interactions except for gauche. We know the HH interactions are gauche for 0 kilocalories. H-methyl is gauche for 0 kilocalories. The only one that we really have to worry about would be methyl-methyl gauche, and we simply don't have that in this conformation. So it's very easy to say that this conformation, as we predicted, the anti-conformation, I'll just write conf, clocks in at exactly 0 kilocalories per mole, and it's pretty obvious why we call this one the lowest possible energy conformation. There's one more conformation we need to look at, or maybe 2, where we have methyl red eclipsed with an H. And there are 2 possibilities of doing that if we keep methyl blue in the same position. There's one here, and of course there's one here. What are we going to do about the fact that we have a bad methyl H interaction here and a bad methyl H interaction here? We need to be able to keep track of that. And according to our energy chart, our H-methyl eclipsed is actually at 1.9, and I think that I've convinced both of you that we have 2 of those. If we remember that we actually have HH eclipsed here, but I'm going to put X's on them because our HH eclipsed actually comes out to be exactly 0 kilocalories per mole. We actually are in a situation where we need to multiply 1.9 by 2 for the two different kinds of methyl red and methyl blue H interactions that are eclipsed. And that gives us our final energy calculation for these two conformations of 3.8 kilocalories per mole. There's that magic XK again. I have no idea where that came from, but I'm feeling a little anal retentive. That looks 1,000 times worse. Please enjoy my handwriting all year long. Question: how the heck are we going to turn all of these energy values into a situation where we can actually plot all infinity possible conformations for butane? It's actually, again, a fairly easy thing to do. Take a look. We're going to generate a chart. Maybe we could generate what I would call a much better chart. I need to give myself just a bit more room. And now this is definitely modeling the way that it usually works when I'm in lecture. And what I'm going to do on the left side is I'm going to chart all the different energy values that we talked about. Of course, ending at the origin with 0. So the y-axis in this case is going to be energy based on kilocalories per mole. What do we have down here on the x-axis? What we could do here is actually talk about some dihedral angles, and that'll give us a chance to talk about those as well. What I'm going to do is I'm going to chart the 60-degree dihedral angles between methyl red and methyl blue so we all know exactly the same conformation that we're talking about here. You remember we called the 180-degree difference the anti-conformation. And of course we can keep going all the way up to 300. And I think everybody is well aware of the fact that 360 degrees is the same as 0 degrees when we're actually plotting that sort of stuff in geometry. So these angles, or thetas if you will, are with regard to methyl blue and methyl red. And that's important because without a frame of reference, we have no idea what functional groups we're referring to. However, we did start out by saying that when they were eclipsed with each other, that is 0 dihedral angles degrees away from each other, they clocked out at about 4.5 kilocalories per mole. And that makes the plotting of the point for that conformation go here. When we're talking about them being 60 degrees apart, they really only have a gauche interaction, and that clocks in at about 0.9, so I'm going to put it close to 1. When we go to 120 dihedral angle degrees, we end up with a double eclipsed methyl blue and an H and methyl red and an H, and that came in at about 3.8. I need to make a bigger dot here. 180 was wonderful because, of course, we were in the anti-conformation, and that clocked in at exactly 0 kilocalories per mole. And then we basically had a repeat of those different conformations looking here, 240 degrees apart if we continue in the positive direction. You could have also called it negative 120 if you wanted to. We would also, again, be at 3.8. And then, of course, for 300, we go down to around 1. And then if 360 and 0 are the same, we'd be back to 0.5. I am very well aware of the fact that, at least in this case, we plotted 7 points, 2 of them are exactly the same, that we have only drawn 7 or 6 points based on your perspective. But if all we do is connect these points and assume that this one continues on and goes around the 360 degrees, goes back to 0 degrees, we have actually plotted all infinity possibilities and the energy levels associated with them for every single conformation of butane. What we need to do is realize that there are an infinite number of different conformational possibilities in isomerism and how exactly we represent them in 3 dimensions and in 2 dimensions when we're drawing different things on paper, on the computer, and using our model kits. Obviously, the most important thing for you to do right now is to practice using your model kit using the sapling homework and the handouts you're going to get today. Again, in summary, These two spots correspond to methyl-methyl eclipsed, which of course makes this spot down here the anti-conformation. What we have here and here are methyl H eclipses, and we have 2 of those per structure, here and here. In these 2 data points, what we're looking at is something a little less threatening, right? All we really have is a methyl-methyl, again, methyl blue, methyl red, gauche interaction. And we can see how if you follow the line, as we start here with methyl-methyl being eclipsed with each other, the energy goes down quite a bit as they become gauche, but as they start becoming eclipsed with other H's, the energy goes up, not all the way back to where we started, but to a really large amount, and then as that energy is released, we can get to 0 as the 2 methyls are as far apart as each other as possible. The pattern repeats itself in the opposite order, getting us back to the 2 methyl groups being eclipsed with each other. It would be wise for you to annotate your notes by drawing the very, very specific Newman projection that corresponds to each one of the data points on this so that you understand exactly how that job is done. I really appreciate you guys putting up with this kind of lecture. I know that usually when the prof's out of town, it's all about freebie time. Remember, I was a student at UDM so many moons ago as well. Not so much at the beginning of organic chemistry. She is a harsh mistress. We need a lot of work to be able to conquer these early subjects, and I did not want you guys to lose out. I promise you I'm still available by talk, text, and tweet like I usually am, and email, and I'll be back in my office Wednesday morning, God willing, as long as the roads are clear, driving back from Indianapolis, and I will see you then. Please make sure you grab the handouts before you leave class. If you haven't turned in your problem set already, make sure you give it to Jane in the main office, and I will see you guys as soon as I can. Thanks for your patience, and see you soon.